Hello, good morning. So today our topic is hydrodynamics. So in hydrodynamics what we will study? We will study rate of flow, then streamline motion, turbulent motion, critical velocity, Bernoullis Theorem, Stokes formula and applications of Bernoullis Theorem. So let us start our journey. Rate of flow. Rate of flow. Rate of flow, how to define rate of flow? Suppose मेरे पास एक ट्यूब है इस टाइप का, ये किस तरफ का ट्यूब है, ये किस टाइप का ट्यूब है, यूनिफॉर्म क्रॉस सेक्शनल एरिया. ओके, we may have a tube like this, इस तरह का भी ट्यूब हो सकता है. दिस इज व्हाट नॉन यूनिफॉर्म क्रॉस सेक्शनल एरिया ट्यूब. ओके, सो now to flow water, we know that for the flow of liquid it flows from higher level to lower level. Okay, and if we want to flow the liquid from lower level to higher level, we have to maintain some pressure. Okay, through pumping station we can do this thing. Now what is rate of flow? Rate of flow क्या है कि पर यूनिट टाइम पे, मतलब पर सेकेंड में जितना मास ऑफ लिक्विड फ्लो होता है, ओके, द मास ऑफ लिक्विड फ्लोइंग पर सेकेंड is called rate of flow. So suppose the cross sectional area is alpha or alpha, suppose, okay, so and the velocity of flow is u. U is the velocity of flow. So in 1 second how much distance this liquid will flow? 1 second में कितना तक जाएगा? Velocity into time. So this will be the distance covered by the liquid in 1 second. Suppose यहाँ तक गया, तो 1 सेकेंड में जितने भी मास ऑफ लिक्विड इस जगह पे प्रेजेंट है, ओके, उस मास ऑफ लिक्विड को कहा जाएगा रेट ऑफ फ्लो. तो कितना होगा मास ऑफ फ्लो? ये हो गया सिलेंडरिकल इन नेचर, इसलिए मैंने पहले रेट ऑफ फ्लो डिफाइन करेंगे एक यूनिफॉर्म क्रॉस सेक्शनल ट्यूब को लेकर. सो व्हाट इज द वॉल्यूम? दिस इज सिलेंडर, so this is cross sectional area into the height. So the volume of the liquid flowing per second equal to alpha into u into 1. Alpha into u into time is 1. Okay, so what is the mass? Mass is volume into density. So suppose rho is the density of this liquid, so what will be the mass? Mass of the liquid flowing per second will be this, alpha into rho into u. So ये जो मास ऑफ लिक्विड फ्लो करता है इसको कहा जाएगा रेट ऑफ फ्लो. सो मास ऑफ लिक्विड फ्लोइंग पर सेकेंड. नाउ सपोज ये नॉन यूनिफॉर्म क्रॉस सेक्शनल एरिया है, तो इसका एरिया अल्फा 1 है, यहाँ पर एरिया सपोज इसका एरिया अल्फा 2 है. तो क्या होगा, जितना भी लिक्विड इसके अंदर जाएगा उतना लिक्विड इसके अंदर से इससे बाहर भी निकलेगा, है ना. रेट ऑफ फ्लो हियर एंड रेट ऑफ फ्लो हियर should be same. अगर सेम नहीं होगा तो क्या होगा? लिक्विड विल गेट एक्यूमुलेटेड, इसके लिक्विड अंदर जाएगा, बस्ट हो जाएगा ट्यूब. सो द अमाउंट ऑफ लिक्विड फ्लोइंग हियर, व्हाट इज द रेट ऑफ फ्लो एट द इनलेट? दिस इज कॉल्ड इनलेट, दिस इज द आउटलेट. आउटलेट. सो व्हाट इज द रेट ऑफ फ्लो एट द इनलेट? अल्फा 1. वेलोसिटी ऑफ फ्लो हियर इज u1 and rho is the density. So liquid is considered to be incompressible. Okay, so density will remain same here. So what will be the rate of flow at the outlet? Alpha 2. यहाँ पर क्या हो जाएगा, क्रॉस सेक्शन एरिया कम है, तो क्रॉस सेक्शन एरिया कम होने से क्या होता है कि वेलोसिटी बढ़ जाएगा. ठीक है, सो सपोज हियर वेलोसिटी इज v2 and density is will remain same here and here. Okay, so alpha 1 u1 equal to alpha 2 u2. So for a liquid flowing in a non-uniform cross-sectional area, so cross-sectional area into the velocity of flow in that region equal to cross-sectional area into velocity of flow in any region. Okay. So wherever the cross-sectional area is less, if alpha 2 is less, then U2 must be higher, U2 must be greater. So if alpha 2 is less than alpha 1, then U2 should be greater than U1. So wherever the liquid, the cross-sectional area of the tube is less, there the liquid will flow with more velocity, with higher velocity. So you understood what is rate of flow. Now water fluid, anything which can flow. So gases and liquids are called fluid. So in hydrodynamics we study both. Okay, the flow of liquid as well as flow of gas. Okay. Now here we will define some term called streamline motion. Streamline motion. What is this streamline motion? जब दो सपोज ये एक ट्यूब है, ओके, दिस इज अ ट्यूब. सो व्हाट हैपेंस, अगर वेलोसिटी ऑफ फ्लो कम है, अगर कम स्पीड में फ्लो कर रहा है, तो ये लिक्विड एक सिस्टमेटिक फैशन में फ्लो करता है. ओके, दिस लिक्विड विल फ्लो इन ए सिस्टमेटिक वे. सिस्टमेटिक वे मीन्स जैसे ये जो पार्टिकल है, ये जो पाथ फॉलो करके आगे जा रहा है, इसके पीछे वाला जो पार्टिकल वो भी सेम पाथ फॉलो करेगा. ओके, द पाथ फॉलोड बाय द प्रेडिसेसर एंड सक्सेसर आर द सेम. ओके, और यू कैन से इट्स ए स्ट्रीमलाइन कर्व. अगर पार्टिकल यहाँ पर है तो इसका वेलोसिटी ऑफ फ्लो कैसे होगा, इस कर्व के ऊपर आप टेंजेंट ड्रॉ करो. सो दिस विल गिव द velocity of the particle. If the particle is here, so if you draw a tangent here, you will get the velocity. Okay, so streamline motion is the systematic flow of motion when the pressure difference across the tube is less. Okay, and it follows a rhythm. So in other words, we can say streamline motion are the curve, so that tangent drawn at any point of the curve will give the direction of velocity at that point. Okay, so this is called streamline motion. So we can study the behavior of a fluid, how it flows in a streamline motion. Now if you increase the pressure difference, okay, you increase the pressure difference, so what will happen? The steadiness of the flow, okay, the way it was flowing, that will be lost. वो लॉस हो जाएगा. उसके बाद क्या होगा? The liquid will flow in a zigzag way, in a random fashion. Okay, no rhythm will be followed. It will it will lose its steadiness. Okay, so up to certain extent of velocity, this streamline flow will be maintained. Okay, the steadiness, the rhythm, the systematic way of flowing, that will be maintained. Okay, beyond that velocity, it will lose its steadiness and becomes turbulent. So now there are two things coming. The limiting velocity, that is called critical velocity. Critical velocity. Critical velocity किसको कहेंगे हम? जितने मैक्सिमम वेलोसिटी से लिक्विड को फ्लो करने से लिक्विड स्ट्रीमलाइन मोशन में रहेगा, उसका स्टेडीनेस रहेगा, सिस्टमेटिक वे में फ्लो करेगा. आप सक्सेसर, प्रेडिसेसर का पाथ सक्सेसर follow करेगा. Okay, tangent at any point of the curve gives the velocity of at that point. Okay, that maximum velocity is called critical velocity. Let us say this is VC, critical velocity. अगर critical velocity से भी ज़्यादा flow करेगा तो that motion will be zigzag, that motion will be random. Okay, so if the velocity of the flow is less than the critical velocity, if the velocity of the flow is less than critical velocity, the motion is streamline motion. Okay, as soon as it crosses the critical velocity, the liquid loses all its steadiness, rhythm, and it becomes turbulent. So what is turbulent motion? So hurricane is a turbulent, okay. Tornado is a turbulent motion. Turbulent motion means which is not following any rhythm. So when what is happening? When the velocity is more than the critical velocity, the motion becomes turbulent motion. Okay. Now our next topic is Bernoullis theorem. So we have studied what is Bernoullis theorem. Bernoulli says that as long as the liquid flowing, there are three kind of energy at every point. Okay, suppose we are considering a tube like this. जब तक liquid flow करता है ना, so suppose this is the base, okay, and there is a tube standing. So here at every point the liquid will have three energies. One that is the gravitational potential energy because of its height, because the liquid is in the constant force field of gravity, so that is called gravitational potential energy. We can consider gravitational potential energy per unit mass. Okay, so gravitational potential energy per unit mass, since it is in motion, so therefore it will have kinetic energy per unit mass, kinetic energy. Okay, and because there is a pressure difference, so that liquid is flowing. Pressure difference के चलते जो energy liquid possess करता है, that energy is called pressure energy per unit mass. So gravitational potential energy per unit mass, kinetic energy per unit mass, plus pressure energy per unit mass. This is constant at every point. Here if you add up all these three energy, at this point if you add up all these energies will remain same. Okay. So what is the statement of Bernoullis theorem? As long as the liquid flowing in a tube, the sum of the three energies, okay, at every point will remain same. What are these components, energy components? Gravitational potential energy per unit mass, kinetic energy per unit mass, pressure energy per unit mass. Okay. So this is Bernoullis theorem. So there is I don't think that it is there in your syllabus, how to prove Bernoullis theorem. So if we have time in detail, we can prepare a video to prove this Bernoullis theorem. Okay. We will skip this derivation part presently. So next topic is our okay. So this is one is Bernoullis theorem. Then second part is Newton's laws of viscosity. Okay. Now we'll come to this. We can take some examples of Bernoullis theorem. Then we'll jump to Newton's formula of viscosity. Viscosity is actually liquid internal friction that we'll take up later on. So let us discuss some examples of Bernoullis theorem. Okay. So what is happening? Suppose you have, this gives very good understanding of Bernoullis theorem. Suppose you have from a rigid support you have hanged two light balls, plastic balls. Okay, two plastic balls are hanged from this. Okay. If you blow air in between, like two balls are there, you are blowing air. So what will happen? The ball will come closer, this will come closer, or this will go away. It will be like this. What can happen? Now see what will happen when you blow air. if we blow air, इस बीच में अगर हम एयर को ब्लो करेंगे क्या होगा, इस जगह पे जो एयर है, here we have air, so the velocity of flow of the air, this will increase. Suppose this is E1, so the air will move with a higher velocity compared to the surrounding air, okay, which is outside this ball. Now so here the velocity is E2, cool and calm. This velocity is at this air is not at okay, this is almost at rest, this air, and here we are blowing air. So what will happen, the kinetic energy of air in this region will increase because the velocity is increasing. Now if the kinetic energy is increasing and here the kinetic energy is less, now in Bernoullis theorem we told that the sum of all the energies, kinetic energy per unit mass, pressure energy per unit mass, and gravitational potential energy per unit mass, all will remain same. So let us neglect this gravitational potential energy per unit mass because both are at the same height, so we can assume the gravitational potential energy are same in both the cases. So what is left, we are left with kinetic energy per unit mass, means half m unit mass, so m is 1 E1 square, okay. This is kinetic energy per unit mass at this position, okay. And what is pressure energy per unit mass? P1 by rho. This is the density of air. So this should be equal to same as kinetic energy per unit mass here, U2 square by 2 plus P2 by rho. So as E1 has increased, say this E1 is increasing here because we are blowing here. तो जैसे E1 ज़्यादा हो जाएगा E2 से, P1 should be less than P2, then P1 will be less than P2. इस रीजन का क्या होगा, प्रेशर कम हो जाएगा. There will be a pressure drop here in this region. It means that the pressure is P1, here pressure is P2, here pressure is P2. So अगर यहाँ का प्रेशर कम हो गया, this is the low pressure region formed now. Now if the pressure is less, here the pressure is higher. So we know that the fluid, okay, air will flow from higher pressure to lower pressure. So the surrounding air will rush here. So it will push both the balls together. So what will happen? These balls will come closer. So these two balls will come closer. If we conventionally think, you would think that when we blow air, this will be separated out, but this will not happen like this. What will happen? As we are blowing air, the pressure here is dropped, and the surrounding air is at higher pressure, so both will push the ball, and this ball will come closer. So you understood? So this is called equation of continuity. Wherever the kinetic energy is more, the pressure energy will be less there. Okay. We can take many such examples like venturimeter tube, oxidizing flame, then velocity of reflux. One most important is velocity of reflux. What is this? Suppose you have a container. Okay. Here you have a liquid. Okay. The velocity at which this liquid comes out is called velocity of reflux. The velocity at which the liquid coming out from this outlet is called velocity of reflux. Now what is velocity of reflux? Let us use this Bernoullis theorem and find it. So here we have liquid, so here we have atmospheric pressure plus, this is the atmospheric pressure, plus the height of liquid exerting pressure here at this point. So what is pressure energy? H rho g is the pressure. Okay. So and here the kinetic energy is 0. Here kinetic energy is something. It is coming out with a velocity, say VE, velocity of reflux. Here potential energy is 0. And what is the pressure? Only the atmospheric pressure. Okay. So here we have at this point gravitational potential energy is 0 because particle is the baseline, there is no height. Okay, so let us consider this is the bottom of this container. So at this point A and this is the point B. At this point, what is pressure energy? P0 plus H rho G. This is the total pressure by rho, plus kinetic energy is 0 here. This should be equal to pressure energy P0 by rho. There is no liquid column here. There is no, okay, that is why this H rho G factor will not come at this point B. So this is P0 by rho. This is the only pressure energy at the point B. And kinetic energy per unit mass, means if it is flowing with a velocity VE coming out, so then VE square by 2. Okay. So if we solve this, P0 by rho will cancel out, Hg by rho cancel out. So this is H into G equal to VE square by 2, or the velocity of a flux equal to root over 2gh. So Bernoullis theorem, the equation of continuity, हम लोगों को ये हेल्प कर रहा कि कितना वेलोसिटी से ये लिक्विड इस ओरिफिस से, इस होल से बाहर आएगा. ओके, सो now we apply our common sense. See, if H is more, then the liquid will flow, liquid will come out with higher speed. So as the level of liquid decreases, the velocity of flow also decreases. Okay, so what is the, if we puncture a hole here, then what will be the velocity? This is the height, so you know the height, so it is h by 2. The velocity of flow will be gh only. Okay, so wherever you will puncture a hole, okay, it depends what is the height, and accordingly this velocity can be determined. So velocity of a flux means the velocity with which the liquid comes out from the hole at the bottom of the container, and it is equal to 2gh. We will take another example, oxidizing flame. See, oxidizing flame means what? Suppose you have a gas here, so that comes, and there is a hole at the, this is a burner, okay, you have a gas supply here, gas supply. So how oxidizing flame gets created means oxygen, atmospheric oxygen rushes inside the tube, correct? So what is happening here? As the gas comes inside this tube, the velocity of air inside the tube increases. So the kinetic energy increases. Here the kinetic energy is more than the kinetic energy of the surrounding. This is inside. So what is happening? The pressure is dropped here. Pressure energy should be less as per the equation of continuity. If pressure is less, this atmosphere is at higher pressure. So what will happen? Atmospheric will rush. ये atmosphere का जो air है इस hole के through अंदर आ जाएगा, and this will get mixed up with this gas and we will get a flame like this. So this is what the oxidizing flame works. Means if someone asks you कि ऑक्सीडाइजिंग फ्लेम में एयर बाहर का एयर क्यों अंदर आता है, इसलिए अंदर आता है क्योंकि जब इनसाइड में जो एयर फ्लो हो रहा उस एयर का वेलोसिटी ज़्यादा है, काइनेटिक एनर्जी इज मोर, pressure energy will be less, so pressure here is dropped, it is at low pressure, atmosphere is at higher pressure, so there is a pressure difference, so atmospheric air will rush inside this. And then see, there is a natural lift, uplift given to the aeroplane. So these are the wings of this aeroplane. Suppose this is an aeroplane, okay. So these are the wings. The wings are designed in such a way that whenever it runs in the runway, so what happens? This velocity of air this is design at the wing of this plane. So the velocity of air on the top of this wing is more. Okay, so what happens? Pressure will be less. So and the air below these wings is at a higher pressure. So what will happen? And velocity is also less below this wing because of this design in this wing. So as it runs in the runway, this plane, what is happening? The air speed at the top of the wings are more than compared to the air below this wing. So here kinetic energy is more, pressure energy is less at the top. So pressure energy is more at the, pressure is more at the bottom. So what will happen? The air will blow from the bottom to the top. So this gives a lift, natural uplift. So this creates a natural uplift. So without using any mechanical device to generate this uplift, we are getting a natural uplift. So this is again because of this velocity is higher, pressure drops, and you get an uplift. One more example I can give you. See, suppose this is a running train. So normally passengers are asked to stay far away from this running train. There is a yellow in the platform, you may have seen there is a yellow line marked. Passengers are asked to stand, okay, away from this yellow line. Why? Why it is so? So when the train comes, or any passenger train or goods train, whenever it comes, the air speed here in this region is more. Okay, air starts flowing with the velocity of this train. So what happens? The pressure decreases. Here pressure is less, and you are standing here. Suppose here the pressure, initially the pressure at the railway track and pressure below behind you were same, but now there is a pressure difference. Why? Because this air is flowing with higher speed, so there is a pressure drop. It is a low pressure region, and behind you, तुम्हारे पीछे क्या हो गया कि जो एयर है उसका वेलोसिटी कम है, तो वहाँ पर प्रेशर ज़्यादा हो गया. तो क्या होगा? तुम्हारे पीछे से एयर क्या करेगा? फ्लो करना, एयर फ्लो विल स्टार्ट. So you may suddenly feel a jerk which will push you towards this running train. Okay, so this is also explained using the Bernoullis theorem of continuity. So that is the reason you should not stay close to the running train. Now we will study one more topic called viscosity. Viscosity is actually liquid internal friction. Okay, liquid internal friction. Internal friction of a liquid. To understand viscosity, let us take a capillary tube. Capillary tube means a tube having very less diameter, hair-like diameter. So we will show this capillary tube in a magnified way to make you understand what is viscosity. So as the liquid flows, we can imagine this liquid is made up of many coaxial cylindrical layers. This is one cylindrical layer. Okay. This is our imagination. So we can imagine this liquid is made up of many such cylindrical layers. Okay, coaxial cylindrical layers. Now, the velocity of this liquid layer, which is along the axis, this is more. Okay. As you go up, this layer will have a less velocity. This layer will have still lesser velocity. Similarly this, similarly this. So ultimately the velocity is such that the sum of the liquid sticks with the wall of this tube. Okay. So this, why this change in velocity? There is a velocity gradient. What is gradient? The change of any parameter with distance is called gradient. So if here the velocity is u1, here the velocity is u2. So u1 minus u2 is delta u, u1 minus u2. And if the distance is suppose delta x between these two, so then delta u by delta x, okay, is called the velocity gradient, the rate of change of velocity of layer along with the distance. Okay. So Newton said that why this is happening? Because this liquid, when the liquid flows, then liquid experience a internal frictional force, and frictional force is always in the opposite direction of motion. Okay. So if you go in this way, so you will face a frictional force along this. This is called fluid friction. Okay. This is called viscosity. Okay. So Newton said that the viscous force is proportional to the area, and viscous force is proportional to the velocity gradient du by dx. If delta x is very less, tending to 0, delta u will be tending to 0, so using calculus we can write it as du by dx, okay, applying the limit. So if there is more velocity gradient, if the rate of change of velocity is more, then we understand that the viscous force is more. Okay. So on which this viscous force, liquid internal force depends? It depends on the area of cross section. Higher is the area, higher will be the viscous force, and it depends also proportional to the velocity gradient. So if we combine both, so then we can say that the viscous force is proportional to the area and the velocity gradient. Okay. To replace this constant of proportionality, let me rub it. अभी जहाँ जहाँ प्रोपोर्शनलिटी साइन आता उसको हम लोग क्या करते हैं, उसको रिप्लेस करने के लिए एक इक्वल साइन एंड एक कांस्टेंट लगता है. ओके. सो वी कैन रिप्लेस दिस प्रोपोर्शनलिटी कांस्टेंट by taking its equal sign and constant. So this is the replacement of proportionality sign. Wherever there is a proportionality sign, we replace it by some constant and equal sign. Okay, into a into du by dx. In some cases it is represented as a negative sign is also given. Negative sign indicates that the velocity of flow and the force are in opposite direction. So you can take a negative sign. This, you can understand negative sign in this way, that the central layer is having maximum velocity, then the upper layer, then the velocity gradient, as we go up the velocity decreases. Okay, and this is the reason we have this negative sign. So the negative velocity gradient, as we go up the layer, as the radius of the layer increases, okay, the velocity of the layer decreases. So this constant of proportionality is called eta. This is called, pronounced as eta. This is called coefficient of viscosity. Coefficient of viscosity. Coefficient is spelling correct? CI, no? Correct? CIENT, okay. So eta is coefficient of viscosity. Okay. Now, eta depends on what type of fluid you have taken, what type of liquid it is. Suppose you have taken glycerin or alcohol or water, so the property of that fluid determines eta. So what is eta? Eta is the nature of fluid. Okay, it signifies the nature of fluid. So what is dimension of eta? Eta, if you keep neglect the negative sign, so F by A into dx by du. So if you want to find out the dimensional unit, force has dimension mLt to the power minus 2 kg meter per second square. Dx is nothing but distance L. Area is meter square, so it is L square. Du is velocity, meter per second, L to the power minus 1. So L square cancel out. Okay, 1 L left and to the power minus 2, and this becomes to the power minus 1. Okay, so it is L A, okay, M L to the power minus 1 and minus 2 plus 1, so T to the power minus 1. So this is the dimension of eta. So what will be the unit of eta? The unit of eta is kg per meter. L to the power minus 1 means per meter per second. So this is what is Newton's formula of viscosity. Correct? So in our next video, we will study about Stokes formula. Okay, rate of flow, streamline motion, turbulent motion, Bernoullis theorem, viscosity, Newton's law. Stokes formula we will study in our next video. This is the flow of liquid. Keep note of it. This is streamline motion. We have seen in streamline motion, it can be defined as the curve tangent at which gives the velocity at that point. Then then this is critical velocity, and critical velocity is defined by the expression called Reynolds formula. Osborn and Reynolds gave this formula, that critical velocity depends on eta, coefficient of viscosity. It depends on the density of this fluid and radius of the tube. So Vc, the critical velocity, is k eta by rho r. This is very important. Critical velocity expression, k eta by rho r. So if r is more, the critical velocity will be more. Means to attain that critical velocity, because if r is more, critical velocity is less. Okay, this is reciprocally related. K is the Reynolds number, rho is density, eta is coefficient of viscosity. Okay, so it is reciprocally related. So if you have a tube of higher radius, there the critical velocity will be less. It means that with small pressure difference, the liquid will lose its steadiness and becomes turbulent. Okay. Because the disorder will increase. So here we have Bernoullis theorem. So actually in this note I have proved this three energy, the sum of three energies come here. Sum of three energies, that is potential energy per unit mass, kinetic energy per unit mass and pressure energy per unit mass, are all constant at every point. So if we get time, we can derive even this expression, but I don't think this is in your course syllabus right now. So you can omit, you can neglect this part of it. So these are the examples of Bernoullis theorem we have seen. If we blow here, it will come closer. So velocity of a flux, this is how we calculate at what velocity it will come out. So later on, when we will do the joint entrance examination, questions and answer, numerical solving or objective type solving, then there are many questions asked from this particular topic, okay, application of Bernoullis theorem. So we will go into the depth of this topic there. So oxidizing flame, there is one more important venturimeter tube. So what is happening in venturimeter? So there is a disconnection between the liquid content inside and the air blowing, okay. So in a venturimeter, what happens? This is one more important part we lost actually. So there is, suppose you have a pump, okay, there is a pump. There is a small orifice here, and the liquid is here, okay. Liquid is connected with this. Now as you blow this, as you push this handle, what happens? The air begins to flow with higher speed as you pump. So what is happening? The speed is more here, so pressure will be less here. So pressure inside is more, so therefore the liquid comes out and joins, and then it gets spread up. Okay. So how the liquid comes up from this container? Because of the pressure difference we are creating. How we are creating pressure difference? By increasing the kinetic energy on this space. And there are other calculations also that we have not discussed, that if you have a liquid and at different intervals at different places, how much liquid will rise inside this tube. So when we'll solve these numericals, study about this. This is viscosity, fluid motion, Newton's laws of viscosity, okay, we derived it. And what is coefficient of viscosity? Here actually, while we define this viscosity, so we defined as F is equal to minus eta A du by dr. Du by dr, du by dx, anything you can write, okay. So how it can be defined? If A is 1, du by dx is 1, then F equal to eta, you neglect the negative sign. So the viscous force acting on a unit surface area having unit velocity gradient is called the coefficient of viscosity. Means if A is 1, du by dx is 1, then F is equal to eta into 1 into 1, so F is equal to eta. So that viscous force which is acting on a liquid producing unit velocity gradient on unit surface area is called the coefficient of viscosity. This is mathematical definition of viscosity. So we have already derived this CGS unit, and CGS unit is grams per centimeter per second. Then we will study in our next video, we will study about Stokes formula and its applications. Terminal velocity, everything will come. Thank you very much.